بسم الله الرحمن الرحيم. الحمد لله رب العالمين، والصلاة والسلام على سيدنا محمد وعلى آله وصحبه الطاهرين. Good evening, my dear students. In the lecture 1, in each first part, the last point we talked about was about challenges related to distributed systems. So, distributed systems are considerably more complex than monolithic computing environment and raise a number of challenges around design, operations, and maintenance. This include five main challenges, which are increasing opportunities for failure, synchronization process challenges, imperfect scalability, more complex security, and increasing complexity. First, what we mean by increasing opportunities for failure. So, the more system added to a computing environment, the more opportunity there is for failure. If a system is not carefully designed and a single node crashes, the entire system can go down. While distributed systems are designed to be fault tolerant, that fault tolerance isn't automatic or foolproof. The second challenge is about synchronization process challenges. Distributed systems work without a global clock, requiring careful programming to ensure that processes are properly synchronized to avoid transmission delays that result in errors and data corruption. In fact, in a complex system, such as a multiplayer video game, synchronization can be challenging, especially on a public network that carries data traffic. The third challenge refers to imperfect scalability. So, doubling the number of nodes in a distributed system doesn't necessarily double performance. So, architecting an effective distributed system that maximizes scalability is a complex undertaking that needs to take into account load balancing, bandwidth management, and other issues. The fourth challenge is about more complex security, which means that managing a large number of nodes in a heterogeneous or globally distributed environment creates numerous security challenges. So, a single weak link in a file system or larger distributed system network can expose the entire system to attacks. The last challenge addresses the problem of complexity or increasing complexity. So distributed systems are more complex to design, to manage, and to understand than traditional computing environments. Now let's address the concept or the principle of a parallel architectures. As you know, these architectures or choosing a specific architectures depends on the intersection of the data stream and the instruction streams, which can be one or many. So if a data stream 1 and the instruction streams 1, here we call or we talk about the SISD architecture, which means traditional one normal single CPU computer. In the second type of architecture, which refers to MISD, which is a data stream as 1 and instruction stream as many. So for the MISD, maybe planet computers. The third kind of architectures, which is the SIMD, which is a many of data streams and one of instruction streams, which refers to a vector processors, fine-grained data, and parallel computers. The last type, with many data streams and many instruction streams, refers to MIMD, with based on a multi-computers and multi-processors. Let's detail now each architecture. In fact, parallel computing is a computing where the jobs are broken into discrete parts that can be executed concurrently. Each part is further broken down to a series of instructions. Instructions from each part execute simultaneously on different CPUs. So parallel systems deal with the simultaneous use of multiple computer resources that can include a single computer with multiple processors, a number of computers connected by a network to form a parallel processing cluster or a combination of both. Parallel systems are more difficult to program than computers with a single processor because the architecture of parallel computers varies accordingly, and the processes of multiple CPUs must be coordinated and synchronized. Okay. So the crux of parallel processing are CPUs. Based on the number of instruction and data streams that can be processed simultaneously, computing systems are classified into four major categories: SISD, MISD, SIMD, and MIMD. Let's start by the first class of this the SISD architecture, which refers to a single instruction, single data. And SISD computing system is a unique processor machine which is capable of executing a single instruction operating on a single data stream. In SISD, machine instructions are processed in a sequential manner, and computers adopting this model are popularly called sequential computers. Most conventional computers have SISD architecture. So all the instructions and data to be processed have to be stored in a primary memory. Okay. So the speed of the processing element in SISD architecture or model is limited or dependent by the rate at which the computer can transfer information internally. Dominant representative SISD systems are, for example, IBM PC or workstations. This is for SISD. Now, let's talk about the second architecture or the second model, which is SIMD, and which refers to single instruction and multiple data systems. An SIMD system is a multiprocessor machine capable of executing the same instruction on all the CPUs, but operating on different data streams. So machines based on an SIMD model are well suited to scientific computing since they involve lots of vector and matrix operations, so that the information can be passed to all the processing elements known as PES. Organized data elements of vector can be divided into multiple sets and sets for NPE systems. And each PE can process one data set. So, as explained for this model, we need a lot of processors. And this is the reason why this architecture or this model is based on a multi-processor machine. The third kind or the third model of architectures, which is MISD, and which refers to multiple instruction, single data systems. An MISD computing system is a multiprocessor machine capable of executing different instructions on different PES, but all of them operating on the same data set. So the system performs different operations on the same data set. Machines built using the MISD model are not useful in most of the application. So a few machines are built, but none of them are available commercially. The last model, which is the MIMD, and which refers to the multiple instruction, multiple data systems. An MIMD system is a multiprocessor machine which is capable of executing multiple instructions on multiple data sets. HPE in the MIMD model has separate instruction and data streams. Therefore, machines built using this model are capable to any kind of application. Unlike SIMD and MISD machines, PS in MIMD machines work asynchronously. So MIMD machines are broadly categorized into shared memory, MIMD, and distributed memory, MIMD, based on the way PS are coupled to the main memory. And let's explain these two categories, which are the shared memory, MIMD, and the distributed memory, MIMD. In the shared memory MIMD model, tightly coupled multiprocessor systems, all the PS are connected to a single global memory, and they all have access to it. The communication between PS in this model takes place through the shared memory, modification of the data stored in the global memory by one PE is visible to all other PEs. Dominant representative shared memory MID system are silicon graphics machines and Sun IBM's machines, or the symmetric multi-processing. So this is for the shared memory MIMD. For the distributed memory MIMD, in this kind of machines, loosely coupled multiprocessor systems, all PEs have a local memory. So the communication between PEs in this model takes place through the interconnection network, which is known as the inter-process communication channel, or IPC. So the network connecting PEs can be configured to tree, mesh, or in accordance with the requirements. The shared memory MIMD architecture is easier to program, but is less tolerant for failures and harder to extend with respect to the distributed memory MIMD model. Failures in a shared memory MIMD affect the entire system, whereas this is not the case of the distributed model, in which each of the PEs can be easily isolated. Moreover, shared memory MIMD architectures are less likely to scale because the addition of more PS leads to memory contention. So this is a situation that does not happen in the case of distributed memory, in which each PE has its own memory. As a result of practical outcomes and users' requirement, distributed memory MIND architecture is superior to the other existing models. Now, let's highlight some advantages of distributed systems. As explained before, a distributed system is a computing environment where work is distributed among multiple components that collaborate to solve a particular problem. Here, the components are separated, but they interact with each other and appear as one single system to the end user. So let's summarize the main advantages of the distributed systems. We can talk about low cost compared to supercomputer price. We can talk about computing and storage power. We can talk about computing and storage performance. And we could talk also regarding reliability and fault resistance. So distributed systems have a myriad of advantages that make their use popular. A few important ones include the improving performance and scalability, also increasing fault tolerance, enhancing reliability, and also the geographic flexibility, the cost effectiveness, the data sharing, and time effective. We can also add advantages regarding complexity or increasing the cost of setup, and also security vulnerabilities and difficulty in debugging and troubleshooting, and data loss or overloading due to network dependency. Okay. Here it's important to explain each advantage. For example, for improving performance and scalability, distributed systems can handle large amounts of data and high user loads by distributing the workload across multiple machines. For example, a distributed web server can handle more concurrent user requests by distributing them across multiple servers. The second advantage, which is increasing fault tolerance. Distributed systems are more resilient to failure as they can continue functioning even if individual components fail. For example, a distributed database can replicate data across multiple nodes, ensuring data availability even if some nodes go offline. The third advantage is about enhancing reliability. So distributed systems can provide reliable services by replicating data and services across multiple nodes. For example, a distributed file system can store multiple copies of files on different machines, reducing the risk of data loss. The fourth advantage refers to geographic flexibility. Distributed systems allow for data and services to be located in different geographical locations. This, in fact, enables organizations to have a global presence and serve users in different regions. For example, a distributed content delivery network, which is called CDN, can catch and serve content from servers located in various countries, reducing latency for users. The fifth advantage, which is the cost effectiveness. So they have a high cost of implementation, distributed systems can be cost effective as they can utilize commodity hardware and distribute the workload across multiple machines. This, in fact, reduces the need for expensive high-end hardware and can lead to cost savings. For example, a distributed computing system can utilize a cluster of low-cost machines instead of a single expensive supercomputer. Advantage number 6, which is the data sharing. The distributed systems enables a component to share data easily with other components of the system. This is possible because in a distributed system, nodes are interconnected for collaboration purposes. Advantage number 8, which is the time effective. As you know, in today's world, time is an important constraint for business personnel and user alike. Distributed systems provide a low latency rate. For example, consider a user who uses the internet and loads a website. So the system makes sure that the node located closer to the user is used to perform the loading task to save time. However, it's sufficient to say that distributed systems are highly efficient as they involve multiple computers that save time for users. Also, they can provide higher performance as compared to centralized systems. On the other hand, it is important to highlight some disadvantages of distributed systems. So some issues occur while using distributed systems. So the important disadvantages can be summarized in 5 main disadvantages. The first disadvantage is about complexity. As you know, or as explained, distributed systems are more complex than centralized systems due to the need for coordination and communication between multiple nodes. For example, in a distributed database system, ensuring data consistency across multiple nodes can be challenging and a real problem. The second advantage is about increasing the cost of setup. So, building and maintaining a distributed system can be more expensive compared to a centralized system. For example, deploying and managing multiple servers in a distributed cloud computing environment can incur higher costs than using a single server in a traditional data center. The third advantage refers to security vulnerabilities. Distributed systems can be more susceptible to security vulnerabilities due to the increased attacks surface and the need to secure communication between nodes. So, ensuring that messages exchanged between nodes remain confidential and intact in a distributed messaging system can be very difficult. Disadvantage number 4 is about difficulty in debugging and troubleshooting. So, identifying and resolving issues in a distributed system can be more difficult compared to a centralized system. For example, diagnosing performance problems in a distributed application can require analyzing logs and metrics from multiple nodes. Okay. The last disadvantage is about data loss or overloading due to network dependency. There can be instances between the data sent from one node to another node can be lost midway in its journey from the source node to the destination node. This results in some important messages being lost, which is detrimental to a company. So, a distributed system can experience overloading if all nodes attempt to send data at the same time. Okay. Now, let's talk about the creation of a grid computing, and which can be based on two approaches. The first approach is based on one or more servers, and the second one is based on one or more clients. In fact, a server is a computer that provides information to other computers called clients on the computer network. This architecture is called the client-server model or the client-server architecture. So servers can provide various functionalities often called services, such as sharing data or resources among multiple clients or performing computations for a client. A single server can serve multiple clients, and a single client can use multiple servers. A client process may run on the same device, or many connect over a network to a server on different devices. A typical servers are database servers, also file servers, mail servers, print servers, web servers, game servers, and application servers. So client server systems are usually most frequently implemented by the request response model. So a client sends a request to the server, which performs some action and sends a response back to the client, typically with a result or acknowledgement. Designating a computer as server class hardware implies that it is specialized for running servers on it. This often implies that it is more powerful and reliable than standard personal computers. But alternatively, large computing clusters may be composed of many relatively simple, replaceable server components. Okay. Now, let's talk about the different types of grid computing, and which are mainly information grid, storage grid, and computing grid. Within a grid computing network, one of the computers acts as the controller that assigns tasks to the rest of the computers. In a grid computing settings, all computers can communicate with the control computer, but not with the other computers in the network. Okay, let's start now by the first type, which refers to the computational grid network, or the computing grid. A computational grid computing network consists of high performance computers such as supercomputers. Computational grids are best for time-sensitive applications. For example, a computational grid can speed up a company's business report generation within seconds, or modify stock market predictions in real time using the nodes in the network with high computational power. This results in a huge performance increase over traditional systems. The second type, which is the scavening grid computing. CPU scaling grid networks have many regular computers as well as a few high-performance ones. Scaling describes the process of searching for available resources in a network of regular computers. We also call this type of grid network CPU scaling or cycle scaling. So CPU scaling networks allow users in different geographical locations to access documents simultaneously. For example, users can access and edit documents, designs, and other files simultaneously. While this may sound similar to how you collaborate with your coworkers through a program like Google Drive, there are key differences. Google is a service provider, so people pay to access the data, and we can do it from any device through web browsers. However, grids are organization-based, and individuals don't pay for them because they are within an organization. Also, grid services are less accessible, so you can only access them through middleware. Likewise, grid computers are also much less scalable than cloud infrastructure. The third type of grid computing refers to storage grid or data storage grid network. So, a data storage grid is a network connecting computers in order to provide large data storage capacity that users can access easily from any node in the network. We might use a data storage grid when we need to coordinate sharing data access between all users in the grid network. We can use this type of grid network as storage for websites with a global user base, such as universities and research institutes. So this is mainly the different type of grid computing. Now, let's talk in details about the computing grid, and which is based on virtual supercomputing, metacomputing, and internet computing. What we mean by a virtual supercomputing? A virtual supercomputing within a supercomputer is scalable tool enabling modification of interconnect topology, computational resources, and components of a virtual supercomputing cluster without the need of stopping computation running on the cluster, taking the whole cluster down. This kind is applicable in development of topology-aware communication algorithms study of impact of interconnect topology on computational problems and performance, and most importantly, discovery of topologies of interconnects tailored for particular computational problems by resources and interconnect adjustment while the computational problem is running on the virtual supercomputing cluster. This is for the virtual supercomputing. Now let's explain the meta computing concept. Meta computing is a computing concept that involves the integration of multiple distributed computer resources to perform complex tasks or solve a large-scale problems. It typically involves the use of advanced networking technologies or parallel processing and coordination techniques to create a virtual supercomputer. Meta computing enables researchers and organizations to leverage the aggregated power of individual computers, which can improve computational efficiency and reduce the need for costly dedicated supercomputing. Here is also important to mention that metacomputing is an important technology terms as it refers to the concept of harnessing the collective power of multiple geographically dispersed computer resource to address complex computational tasks. This approach enables researchers and organizations to tackle large-scale problems that are often impossible to solve using traditional computing methods. By utilizing advanced software techniques, including distributed computing, grid computing, parallel processing, metacomputing surpasses the limitations of individual systems and promotes collaboration between researchers across the globe. In various fields, such as scientific research, data analysis, and high-performance computing, metacomputing plays a pivotal role in achieving large-scale computational capabilities. One key example of metacomputing application is in computational grid systems, which essentially act as decentralized supercomputers linking numerous computers together to solve complex or compute-intensive problems. So, by leveraging metacomputing, researchers can perform intricate simulations, process massive data sets, and create sophisticated models, all of which would be impossible with traditional computing resources. In conclusion, meta computing enables users to surpass the limitation posed by individual computers and networks, providing unparalleled computational power that accelerates advancement in multiple domains, from scientific exploration to business analytics. The last concept of computing grid is the internet computing. Internet computing is a model for enabling convenient on-demand network access to a shared pool of configurable computing resources. For example, networks, servers, storage, applications, and services that can be rapidly provisioned and released with a minimal management effort or service provider interaction. This internet model promotes availability and is composed of 5 essential characteristics, in which 3 are service models and 4 for the deployment models. For the service models, here we will talk, and in which we will explain in details in the cloud computing chapter, when we talk about the services models as software as a service, infrastructure as a service, and platform as a service. For the deployment models, we will talk also about the cloud the public cloud computing, private cloud, community cloud, and the hybrid cloud. Inshallah, we will talk about these characteristics for service models and deployment models in the chapter of cloud computing. So this is what we have regarding this lecture, which is the second part of chapter 1. I hope, inshallah, these records will be very helpful and useful for you. Enjoy listening these records, and see you, inshallah, in the next lecture. Assalamu alaikum wa rahmatullahi ta'ala wa barakatuh.